Our first lab assignment. This is a really cool assignment. We're going to get to do some data mining from NASA's GISS, the Goddard Institute for Space Studies webpage, where they run a whole bunch of different climate models and present the data for us to use. So you're going to make climate maps, basically. You're going to download some NetCDF files. NetCDF means Network Common Data Form. It's like a multi-dimensional file format. Think of a raster that instead of only being able to contain one value for every cell, it's sort of a data format that can store multiple variables at once. They're typically really large files, but you can then subsequently mine the NetCDF file to display smaller subsets of data like temperature, wind speed, wind direction, humidity, air pressure. These NetCDF files are commonly used by climate scientists and by the atmosphere and oceanography communities because of the way they can store these multiple related variables. They're also cool because they're non-proprietary, so they can be used by different software and different operating systems. They're not an ARC thing, which is great. Okay, so you're going to make global maps of temperature change. Second, you're going to create a new web page on your website to house this particular assignment, and then you're going to publish everything, map and web page. I want you to focus on cartography this week. We're going to open up this conversation about data presentation and science communication. So really focus on the cartography. Make this map stunning and intelligent. This is a data, an example or a visualization of the data that you're going to be extracting. So this is a model run that I did this week, and let's pick it apart a little bit. So obviously it's a global map. Obviously we've got some temperatures down here. We can see they're measured in degrees Celsius, so that's helpful. But then what's all this stuff? Annual December to November, so a full year, 2020, compared against a baseline period from 1881, which is the earliest period of record that GISS has climate data for, through 1910. Atmospheric scientists like to use 30-year periods, and what they're doing here for us is averaging annual temperatures over a 30-year period of time from 1881, pre-industrial, to 1910. Then what they're doing is averaging on a cell-by-cell basis annual temperatures in the year 2020 and subtracting. So we've got this set of time and temperatures, and we're subtracting on a cell-by-cell basis the annual temperatures over this 30-year period from these temperatures. And what's being mapped is the difference. So that's what anomaly is. It's the change. It's the difference in surface temperatures between this period of time and this period of time. The global average is an increase of 1.26 degrees Celsius. Gray areas are areas of missing data. The neutral or no change over time is being shown in white, with cool colors denoting pockets of cooling and warm colors denoting pockets of warming. And when I say pockets, I mean global expanse, with a lot of very serious warming in the Arctic, as we all know to be true. But look at these temperatures. I've been teaching this lab for about 4 years, and the scale has never extended past 4. They've just added this. I've never seen the scale go up to 6.9 before. I've run this model many, many times. So I want you to take this information and create a very elegant map showing surface temperature changes, not only over time. So what we're doing here is we're looking at the change between these two periods. I want you to run 2 models. This one is comparing a year, 2020, against this baseline period. I want you to run a second model, maybe an earlier time period, like maybe compare 1950 or 1970 to this early time period. Or maybe you want to run a 30-year period that ends in 2020 It's going to bring these averages down because we're seeing more warming in later years. So our current year has shown the highest temperatures. 2019 slightly less, 2018 slightly less. So if you average a 30-year period, the average is going to come down and you're not going to see a global increase like this. So part of this assignment is to pick a perspective and choose your data timeframes to tell a particular story. If you want to play the role of a climate denier, maybe you use a 30-year period here, which is going to bring these changes down, and it's not going to look quite so extreme. But if you take a 1-year period of time and compare it against a baseline, I want you to pick a second one. It could be 1980 and 2020, each compared to the same baseline period, and then you're going to show the change or increase in warming as time passes. You'll also be given some plots like this to look at. And I just want you to look. You can see that the largest increases in temperature, or changes to the positive, or warming, I should say, not positive, are occurring in the northern latitudes. And we know that. We know that the Arctic is disproportionately warming. At around 60 degrees in the southern hemisphere, there's this region that's showing slight cooling. And, when I say slight cooling, I mean very slight. It's just barely below zero here, or maybe even no change. But there is this weird little dip here. And you can see I've run two 30-year periods against the baseline, that earlier 1880 to 1910. So I ran a model comparing a 30-year period of time from 1950 to 1980 against that earlier period, and a later one, 1980 to 2010. They look the same. The patterns are the same, but check out the y-axes. The values here are maxing out at 1.4, and here they're maxing out at 2.2. So that is a disingenuous way of presenting this data. It looks like there's no change. It would be much smarter to present this data with a common set of values for the y-axis. Okay, this is the kind of map you might make, but it's not just about getting all the details on the page and creating alignments and things like that. You really need to think about the legends. How are you going to present this temperature data? Here, we're using a divergent color ramp where the neutral color is yellow. So if you're telling your audience that there's zero change, but giving it a warm color, you're imparting bias into these climate maps. You're making it look warmer than it actually is. All of these yellow areas are actually areas of no change, but they look like warming. So I want you to really think through the decisions that you need to make to symbolize this data. You can stretch the ramps like this. Why is this one taller? Well, it's drawing your attention to the fact that the maximum value is much larger. I think that's important. You can do this with one legend, but you need to figure that out. Okay, convince me. The objectives for this lab are to convince me that the spatial pattern and the temperature changes that you're showing in your maps are true representations of the data. You don't need to convince me that climate change is real. You need to convince me that your maps are true, accurate representations of the data that's in them. I know this data very well. Number two, I want you to provide detailed context for your map displays. I don't mean that you need to write me an essay, but your website and the maps need to be freestanding. You need to give all the context that's necessary to convince an audience that what you're displaying, I guess you need to provide the meaning for what you're displaying. You need to be clear that the values are a difference over a period of time. Don't make a map telling me that this is surface temperature. Okay, it's not surface temperature. Make sure you understand what this data is. And then make sure you're very clear about what the time periods are. Are they monthly averages, annual averages? Be clear. You know you're doing it wrong when. Just a brief reminder about how not to make maps. Number one, map titles shouldn't reference the assignment. That's very third grade. Don't do that. Titles should articulate what and where. What's the map's purpose and where is it happening? And provide some context. Also, don't use the word map in your map title. It's also redundant and obvious. Make sure you're sizing things appropriately. The scale here is way too big, and I'll talk about this scale in 1 second. Title is way too big relative to the data. Okay, make sure that that there's an intellectual hierarchy that's connected to the visual hierarchy in how you size things on the page. Scale bars need to be rounded and simplified. There's no reason to have a scale bar that spans the entire map. There's no reason to have all these divisions, all these tick marks, all these numbers, and 6,800 is a completely unintuitive number, as is a division of 1,700 feet. Pick the right units so you don't have fractions and so you don't have like ridiculously large numbers, and simplify. It's supposed to be something you look at quickly and get a sense of the scale. Representative fractions, these are incorrect for digital maps. You're going to be displaying these on a website, and this doesn't have any meaning if you change the size of the actual print layout. So this makes sense if you're printing it at 8.5 by 11, and you can actually say 1 inch on the paper is equal to 18,628 inches on the ground. But if you change the size of your display, like zooming in on it on your digital screen or putting it on a PowerPoint, this has no meaning at all. Also, don't ever use these unless you round them, 1 to 20,000, etc. But don't use them. They're going to be wrong 99.9999999% of the time. Okay, what can we do to improve this legend? It's brilliant in that it has the neutral color set to 0. Hooray. But this is unnecessary. This is jargon. This doesn't matter. These need to be rounded, and they don't have any units of measure. So there you go. Again, include text on your web pages to supply context for the assignment and for the maps, and to convince your audience that you are a competent and professional spatial analyst. The 6 C's to earning more than a C. This is something that I learned from Joe Wheaton. Colorful but not cluttered. Creative but not confusing. Consistent. That means like being consistent with your symbology between maps, being consistent with scale, text. Provide context. Be convincing. That means make deliberate choices and evaluate your results and explain to your audience, me, that you have evaluated your results. How do I know that you know you're doing it right? By the time you're in this class, you need to start working as an independent geospatial analyst. You're not always going to have an instructor there to say, oh, your results didn't work out. Surprise. You need to be able to figure out if your results are correct on your own. And hopefully you can understand why. And then correct. So that includes when you publish your website, make sure you're publishing it and sharing it to the public, and all the images and PDFs that you're linking to or displaying in your web pages have to also be published to the public so that they're visible. And that's it. Have fun.